Section 14.3, partial derivatives. So some learning goals: know the definition of partial derivatives, be able to compute them. Also, maybe we can throw in there, know some graphical know the graphical interpretation of the partial derivatives. Know how to compute higher order partial derivatives. Be able to apply Clairaut's theorem. So to start, a little bit of motivation for this. Let's talk about something that maybe you learned in a physics class somewhere, and maybe you don't know this, that's fine. Ohm's law. And so one way that we can write Ohm's law is I is equal to V over R. For those that know, I is current, V is voltage, R is resistance. This has to do with electrical circuits and stuff like that. Again, if you don't know that, don't worry about that. But we're basically, we can think of this, maybe I can rewrite this as I depends on V and R. And so, I mean, you figure out what the voltage is, you figure out what the resistance is, you can calculate the current in this way. I is the current. And so the thing that we should realize here, well, if we increase V, if we increase the voltage, that means that we increase the current, I. But if we increase the resistance, we actually decrease the current. So bigger resistance divided by something bigger, smaller current. And so we see here that the current depends on the voltage and resistance in different ways here. And the question is how to kind of capture this information. And so the way that we're going to capture this information is through partial derivatives. So this is going to be our notion of derivative here in this chapter 14, and then successive chapters. So let me just make something very clear here, that so far, like we've introduced these functions of two or more variables. We haven't had like a way to figure out what the derivative is, and as it turns out, there's no single derivative. We have different partial derivatives. What are these partial derivatives going to be? Partial derivatives are going to be rates of change, WRT, with respect to each variable. And so in particular, for this Ohm's law here, we're going to have a partial derivative with respect to V and a partial derivative with respect to R. We're going to have a rate of change with respect to each variable. So there's no single partial derivative for I. There's two partial derivatives, one with respect to V, one with respect to R. If we have a function f of x, y, you have a partial derivative with respect to x and a partial derivative with respect to y. Okay, so that's the motivation. We need to kind of think about the definition of it. If we think back to one variable calculus, let me squeeze in down here. What's the definition of f prime of x? It's the limit as h goes to 0 of f of x plus h minus f of x divided by h. So you increment x by h here, plug that into f, subtract f of x from it, divide by h, take the limit as h goes to 0. So what we're going to do, let me just go ahead and show this slide here. I've written down we have f of x, y. Up here is the partial derivative of f of x, y with respect to x at a point x naught, y naught. Down here is partial derivative of f of x, y with respect to y at x naught, y naught. That's down here. So let's see what's going on. The partial derivative f of x f of x, y with respect to x at x naught, y naught, what we do is that we increment x naught by h, but we don't increment y naught by h. So y naught is held fixed here. Other than that, f of x naught plus h, comma y naught, minus f of x naught, y naught. So subtract those, we form the difference quotient, we divide by h, and take the limit as h goes to 0 here. Partial derivative of f of x, y with respect to y at x naught, y naught. So now we increment y naught by h, f of x naught, comma y naught plus h, minus f of x naught, y naught. All of that divided by h. The limit as h goes to 0 is going to be the partial derivative here of f with respect to y at x naught, y naught. Of course, we should always note that we have to put the little condition on here. We're assuming that these limits exist. Okay, so let me make some wrap-up comments here on this video before we do the next video. We'll have lots of examples in it. The first is notation. So note here, I wrote this, but I didn't really draw much attention to it. Now let me draw attention to this. So this is the partial derivative of f with respect to x. Note that these are, so this symbol here is a stylized d. So in one variable, we write df dx, but in, Math 251, when we're dealing with functions of more than one variables, we need to indicate that this is a partial derivative and not this kind of derivative. We always should write our d's in the stylized scripty way. And I usually pronounce this, the partial here as partial. So I would say partial f, partial x, or partial f with respect to x. And of course, same thing here for partial f with respect to y. There's actually a second way to do notation. So is you do f sub x. So this is also the partial derivative with respect to x. Here is the partial derivative with respect to y. So this is acceptable notation. This is down here is acceptable notation. You should be comfortable using both forms of these. Let me point out something that is not good notation. And so bad notation is something like f prime of xy. So do not do this. We are used to doing f prime of x is perfectly fine notation if you're dealing with a function of one variable. F prime of xy doesn't tell you are you doing a partial derivative with respect to x or a partial derivative with respect to y? This doesn't tell you how to do that. Okay, so I think that's some notational things. Next video, we're going to do a lot about how to compute partial derivatives and compute a bunch of partial derivatives. And later on, I'll talk about some geometric interpretation. We'll have some nice pictures showing off what's going on with partial derivatives. Okay, but that's our introduction.